Okay, we talked about gravitational potential, and I had this, I said, oh, look, there's force, and there's gravitational field strength, and then there's gravitational potential, and then there's gravitational potential energy. Except I've drawn those the wrong way around. Okay, well, it's the same picture here. So you have the force due to electrostatic field. To get to the field strength, you divide not by mass, but by charge. You can have the electrostatic potential energy. To get to the electric potential, you just divide by charge. And to get between, to cross the aisles, you have to integrate with respect to distance or differentiate with respect to distance. Okay. That sort of square, that rectangle of relations is the same, but you just need to tweak the symbols and the names. A charged particle moving between charged plates along electric field lines has work being done on it by the field. Undoubtedly true. So the work done is the electric field times. No, tell you what, so it's the force times the distance. Our definition of work done is force times the distance moved in the direction of the force. Work done. We've got a cell powering it with a potential difference here, and we've got to be careful a little bit because because voltage. Well, this is an insight into potential difference. The reason potential differences are called potential difference is exactly this. It is this electric potential. It's a difference in this electric potential. Okay, and I said that potential difference is equal to, yesterday this was, I said it was energy per unit charge. Or, in this case, it's work done per unit charge. So work done is therefore equal to VQ. The force, well, that is equal to the electric field strength times the charge. And the separation D, well, the difference, the distance traveled is going to be the distance from one plate to the other. Okay, so we have this equation. Cancel the Q's, and you find that the electric field strength between these plates is V over D. That is an equation that is worth remembering. The electric field strength is equal to the voltage divided, the voltage, literally the difference in potential from one side to the next, divided by the distance between the plates. The electric potential at a point is defined as the work done per unit charge. Yep, so you'll recognize this concept of energy per unit charge is the same as when I was talking about voltage. It is energy transferred per unit charge. I know we've approached both these definitions of potential difference from two different angles, but in your mind, unite them. In bringing, or at least recognize that they're, two sides of the same building. In bringing a positive charge from infinity to that point. Yes. Okay, so potential difference in a circuit is the difference when you're going around the circuit. If we are talking about electric potential more broadly, if they say define electric potential, like gravitational potential, the definition is it's the work done per unit charge instead of per unit mass, the work done per unit charge to bring a charge from infinity to that point. Okay? So, if they are similar charges, they're going to repel, and so you're going to have to force them together. You're going to have to put the work in, which means that the potential will be positive. If they are opposite charges, then actually you're not going to need to do any work at all. The field will do the work. The field will pull them together, which means that the electric potential is negative. So unlike for gravity, we said the potential was always negative. For the case of electric fields, it can be negative, but it can also be positive. Okay. It is also the case, as the slide says, that we had a similar slide for gravity. We said that the work done was, that's interesting, was the area underneath this graph of force over R. And the same is true here. So that's the work done. That is this is equal to the electric potential energy of a charged particle in the field. Yep. Like I said on the previous slides, if you integrate the force with respect to R, i.e. you find the area underneath the graph of force against displacement, you'll get the electric potential energy. That's what this point down here is reminding us of. Right, one more slide and then we might have to skip the question. The work done follows this equation. Again, like gravity, where gravity, the equations for gravitational potential energy and gravitational force were very similar, except that one was 1 over r squared and one was 1 over r. Same story here. If this is the not gravitational potential energy, but the electric potential energy, the work done, then the potential, well, it's just the work done per unit charge. And so it's just, I'll tell you what, let's get rid of a little q and keep a big q. We can use the equation for electric potential to determine the potential difference between 2 points in an electric field. Great. Okay, now we really are getting very close to circuits. Okay, so I've got point A, got a point B. They exist in this complicated field where we've got multiple sources, and they'll sort of be repelling each other a bit. Something like that. With all the arrows going away from my positive charges. Okay. So the potential difference is just that. It is the difference in potentials between VA and VB. So how much work am I going to need to put in per unit charge to move a little positive test charge from A to B? And to work that out, we factor out the charge, because presumably we're moving the same charge. So I think what we were aiming for with this diagram is that this little charge on the right is our test charge. So, you know, I'll put them in brackets. Here's our little test charge. How much work am I going to have to put in to move this positive test charge from A to B? The answer appears on the right. No work is done on a charged particle traveling perpendicular to the electric field. Yeah, that makes sense. Work is only done by a force if you're moving in a direction parallel with that force. So if you're moving at right angles to a field line, then the force will be perpendicular to your motion and you won't do any work.